Hello, Web Summit. Thank you for coming today. Hopefully, you're here because you're interested in learning about graph databases. If you're not, well, maybe you will be by the end of this presentation. My name is Gabe Hollenby. This is a little bit of information about me before we get started. So I'm a technical evangelist with AWS. All that means is I'm a software developer who also likes getting up on stage and talking to people. So I get to go learn about all kinds of cool things like graph databases and then share that with you. So thank you for letting me have the greatest job ever. You're a part of that, and I'm really grateful for you being here today. I have a long history of software development. I've worked at all kinds of companies, written all kinds of code with a lot of different languages. So a real polyglot developer. If you like what I have to say here today and you want to hear more from me in the future, that's my Twitter handle. It's just my name all smushed together, so you can follow me there. Also, don't sweat about the slides. We're going to email you. If we scanned your badge anyway, we're going to email you all the slides for all the decks today. So take a picture if you want, but you definitely don't need to. I know in the back it's a little bit hard to see the bottom edge of the screen, but you'll have access to the slides later. So before we get into graph databases, why should you care about this? Well, this is from dbengines.com. This is a chart of database engine trends over time. And I took this screenshot from their website recently. You can see at the bottom, you might not be able to see the timeline in the bottom, but on the left-hand side, we've got January 2013, and on the right-hand side, we've got up until basically now. And that green circular dot, the big one, is graph databases. So a lot of people are interested in graph databases for good reason. There's a lot of hype, a lot of buzz about them. I mean, there's a lot of you here watching this today if you look around. So I hope that today I can help inform you about when you should care about graph databases, what they're good for, and what they're not good for, and how you can get started using graph databases on AWS. So what is a graph database? It's really just a certain kind of database that's optimized for the efficient storage and retrieval of highly connected data. So there's a lot of different use cases that fall into what is highly connected data. Here are some examples. So the obvious one is social networking, right? We talk about a social network graph. And by the way, when we talk about graphs, we don't mean drawings like the graph we saw in the first slide. What we mean is a graph or a network of data and nodes. So social networking is an obvious example. You have people know each other. It's how you can figure out how many degrees hops away you are from that other person on LinkedIn. Recommendations is another popular use case. So this is the classic things I bought that other people also bought that I rated high. They rated them high. What else did they rate similar to me that I haven't rated yet that I might be interested in? Graph databases are really good at that kind of highly connected data set. Knowledge graphs. So knowledge graphs are ways to encode information about the world into an ontology and represent that as a connected network of data, right? So you could think of kingdom, phylum, class, order, family, genus, species is a knowledge graph of how we all fit into the tree of life. But you can do other kinds of knowledge graphs, and I'll give you an example of one a little bit later. Fraud detection is another really key use case, very popular. People have been doing fraud detection with graph databases for a long time. An example would be answering questions like, I'm a payment gateway processor, and I want to say when a transaction comes in, what are other transactions that look like this one, right? Transactions that have the same IP, or for the same shipping to the same address, or from the same username, or for the same products, or combinations of those things, right? So finding similarities in a network between pieces of data, and because maybe that's fraudulent or not, right? Like there are reasons why it might be. Life sciences, there's a lot of things you can do where you're studying drug interactions with genes and predictive analysis and those sorts of things. And finally, network and IT operations. Well, the name, it's basically in the word, right? Network. We talk about computer networks or networks of software and systems. Well, these networks a network is a graph. And so you can do interesting analysis, things like impact analysis, right? So how many services depend on this one service or that other one, or which are the services that most of my other things depend on. So if those have a problem, what are going to be the cascading consequences? So those types of use cases all lend themselves really well to graph database applications. Let's look at a few more specific examples. So here's a recommendation based on relationships. So in this kind of multi-dimensional setup, we have people who have purchased products, and people also follow particular, like a sport, and then we also have people who know each other. And so with this kind of network, you can not only answer questions like, people who also follow sports purchase this stuff, so you can do a recommendation that way, based not on just like your purchase history, but on other dimensions of commonality. And you can also do things like, well, if the guy on the bottom, the guy on the top knows the guy on the bottom, the guy on the top knows the gal on the left, sorry, on the right, then maybe we can do an introduction there. By the way, this kind of like making a little triangle here, it's called triadic closure. That's just a little bit of jargon for you. And a triangle is the smallest fully connected graph that you can make. And so when you're trying to do these, recommendation things of, do you know so-and-so that you see on like LinkedIn and Facebook and stuff, the way that works in part is by trying to find these new triangles in the graph that you can form and using those to introduce people to each other. On the knowledge graph side, unfortunately, some of this screen doesn't show all the words perfectly, but this says Eiffel Tower, and there's a user who's interested or is in Paris, et cetera. But you can encode different types of data together in a knowledge graph to answer questions like, who painted the Mona Lisa? Or what museum should Alice visit while she's in Paris? Or what artists have paintings in the Louvre? These kinds of questions and many more can be answered if you have an ontology representing the data in the world, and in different types of data too. Now, you can do everything I'm talking about without a graph database. Right? You can do this all with a traditional relational database, an RDBMS. Ironically, though, we call them relational databases, but they're not very good at relations. It's the legacy that we've inherited for oftentimes trying to implement graphs on relational databases, because they've been the workhorse for a lot of database workloads for many years. Just to give you an example, here is a kind of situation that you might have if you have people in a particular department that have built certain products. And on the left is a traditional relational database, ERD, entity relationship diagram that you might have. And on the right is how you might model it in a graph. The difference being, in a graph, the relationships are first-class citizens, right? In an RDBMS, we have join tables and we have foreign keys, but there's no semantic meaning in a join table. It's a table just like any other table. You as a developer have to know, all right, this is the table I go to join these other tables together and find some metadata about this relationship. In a graph database, you have a node, like a circle there, like employee, and you can say from that node what relationships exist broadly. And it'll say, in this case, okay, well, this employee has skills, and this employee knows other employees, for example. So I'll leave it up to you about which one looks more comfortable. At first I thought, oh, well, I'm used to this, the relational database method. So I'm fine, I've been working this way a lot, why do I need to change? Well, because as you scale this stuff up, relational databases aren't meant for this kind of workload, and that's where they fall over. And if we were to talk about this domain that I've modeled on the right, we might go to the whiteboard and draw it out very similarly to the actual graph representation as it's depicted there. And so graph applications also have this nice benefit of, we tend to think about the world and the relationships between our data in a way that's more naturally expressed by a graph than by join tables and foreign keys. So, I mentioned that relational databases have some challenges. Well, to get into more specifics there, they're not really great at querying graphs. The types of workloads that they're good at are not, they can handle 1 or 2 or maybe 3 joins okay, but when you get into typical graph workloads might be doing 5, 6, 7, 8 joins, or what you would do in a relational database as joins, and that's where you're not going to see the same performance characteristics out of an RDBMS. They're just not built for those kinds of I/O workloads. And furthermore, graph databases tend to have more flexible schemas. So I'll talk about this a bit more, but in general, in a relational database, you have your tables and they have a fixed schema. With most graph databases, you have the option of saying, I have two different employee type nodes. One of them has this metadata, first name, last name. One has first name, last name, and interest. So and it's okay if all the schema is more like not rigid between each data type. So let's walk through a quick example of relational versus graph and how you just might implement both. So I talked about recommendations. And so if we say, I want to do a product recommendation, the algorithm for answering it might look like this. Find out what the customer already ordered, and then from that, look and see who else ordered those same products. And then say, OK, what else did those people order? Now, only look at the products that first customer hasn't already ordered, and then sort that in an order by the most ordered products on top, right? Those are probably good things to recommend. And this is one algorithm that might work. That's what it looks like in SQL. It's not awesome. I think that's fair to say. I had to make the font size 7 points for this, which was lower than what the menu in PowerPoint even lets you pick for the font size. So to get it all nicely on one slide, we had to go pretty small font. This is what it looks like in a graph traversal language called Gremlin, and we'll see more examples of Gremlin later in this talk. This is how we might model the domain on the right-hand side. And we're not going to walk through exactly what this query does right now, because I'll walk you through a specific example like this later. But which one would you rather maintain, right? So you can do it in both technologies. One is going to work better and maybe make your life happier. Thomson Reuters is one example customer who's doing interesting things with graph applications. So they have a product that they're working on that lets them navigate global tax policies and corporate structures and how those two things relate together so that they can advise companies on what sort of tax policies they need to be aware of based on the features of those the companies themselves. So you have highly connected data in really complex ways, because tax is never a simple thing. And a graph database is a really natural application for that kind of domain. So now I want to just get you a little bit more familiar with what the nuts and bolts of working with graph databases is like. What does it actually look like? Instead of just showing me a schema diagram of how data is related, how do I query it? How do I model this data? What does it look like? And there are two leading graph models and frameworks that I'm going to talk about today. One of them, the graph framework is called it's a property graph model, and the other one is called the resource description framework, or RDF. I'm just curious from the crowd here, how many people have experience with working with property graphs? Can you put your hand up? Like, good, just a handful. And how about with RDF? Yeah, a bit more. OK, right. So property graph is maybe a little bit more familiar to those who come from a relational database background. It tends to map a little bit easier to your brain. Now, there's an open source Apache project called Tinkerpop. And Tinkerpop does a few different things, but one of the things it does is it offers an imperative graph traversal language called Gremlin. And so I'll show you examples of using Gremlin later. On the RDF side of things, so RDF is a W3C standard, World Wide Web Consortium standard, and they have a query language for querying data represented in RDF called Sparkle. So we'll look into both of those. So RDF, just to go into it first, don't worry about the one on the left, the slide on the right. That's really just to show you that this left-hand side is like a zoomed-in version of what we see on the right. So in RDF, what you do is you model your data with what we call triples. And so it's a subject, a predicate, and an object. And so what I have here on the left is this is actually representing Netflix. So we have this node at the top here that says, this is an organization. It has a particular permanent ID. Everything in RDF, by the way, is like they're URIs, right? All the IDs are URIs. And this makes it really easy to link data together from different data sources. So I have this URI, permid.org/blah, blah, blah, some number. And that represents a company. We can say they have an organization name of Netflix. They have a registered phone number of whatever that is. And then they are incorporated in some other node, which has an attribute of an ISO country code of the US. So the URIs are the unique identifiers, as you can see here. So we have this one on the top that represents the company Netflix. We have this one on the right-hand side, the green one, that represents the country USA. And the relationship organization is incorporated in identifies a relationship as well. I mentioned they're in triples, and so every edge in the graph, if you're working with RDF, has a subject, a predicate, and an object. So the subject is the thing that you're talking about, the predicate is like the relationship, and the object is the thing it's related to. So every edge, or every line between the dots is represented by a triple like this. And you'll notice that the first one up there was the object happened to be another URI, but in this example where we're saying Netflix, the organization name is Netflix, it can be a literal value also, right? So you can say a literal is like a sink in the graph. It doesn't go on and point to some other value. So they're like the leaves of the tree structure. But what is an object for one relation can also be the subject for another relation, right? So that entity representing the United States is a subject for where something's incorporated, an object for where something's incorporated in, and it is a subject describing the country code US. So these four triples that we have here describe the four edges that you see here in this graph. Now, as I mentioned, the real power of RDF and what it was born out of was this idea of the semantic web, right? This really cool idea that if we could standardize how we represent data into certain schemas that are semantically expressive, then we can start linking disparate but related data sets together in really powerful ways. And so if that kind of application is interesting to you, that's where you're going to want to use an RDF-style graph database instead of a property graph, because that's what they excel at. So an example here, right, what we've been working with, we've got like Wikidata is a data source that takes data from Wikipedia and makes it available in a semantic context. So you could take data from that, and maybe from the GeoNames database, which is the thing that represents locations in the world as semantically dependent, consistently ID'd structures. And you can blend them together to answer these queries and model data in a cross-domain fashion. So what does querying look like in RDF? So it's kind of like pattern matching. You describe this pattern, and then the engine figures out what will resolve that pattern in the way that you ask. So here we have a question mark for name. So we say, you're going to see a lot of things that say prefix, and that's because, as I mentioned, these are all XML URIs, these namespaces, and we would blow our brains out if we had to type these namespaces all the time in our queries. So at the top you can say, here are the namespaces I'm working with for this query. I'm going to give them a little shorthand and reference them with that shorthand for the duration of the query. So we say, OK, here's a vcard prefix, and now I want to say select something called name where, and then I give a pattern here. This is an RDF triple pattern, right? Where this perm ID has an organization name of question mark name. So question mark name is that variable, and then what we get back is the result of that from the graph. So it kind of looks like SQL. I mean, there's a select statement, there's a where. It's a little comforting in that way. But from a pattern matching perspective, it's not exactly the same as SQL. You can also say, like I mentioned before, give me all the relationships about a node, right? This is like the key differentiator between a graph database and an RDBMS from a data modeling perspective. The fact that relationships are first-class data means we can say, from a node, select property node, like this pattern, where, and then we say that same perm ID again, and then throw in the second two parts of the three-part of the triple, and we'll get back all of the properties and the nodes that they talk about, right? So that's all the relationships for that node. Furthermore, you can pull out other things. So if I said, all right, I know I'm interested in a company called Netflix, but I don't know its perm ID, you could query it this way. You could say, all right, give me the org and the phone number where the organization's vcard name was Netflix and where the org's phone number is phone pattern. And so these kind of pattern matchings are pretty instinctual, pretty comfortable to work with once you wrap your head around them. You can also hop from one direction to another. In this case, we can say, from this org, I want to know the country that it's incorporated in, and from that, I want to know the ISO country code. That's how we would get the fact that literal value US from the hop. And you can even do really interesting things where you blend data together from different data sets, like I was saying before. So without reading this whole thing, what this query does is it says, find me the companies that have greater than a certain number of employees, and from them, give me the stock ticker names, I'm sorry, the names of the organization in English and in Chinese. So, and that's blending together data from a wiki data set and a feature set for where companies are incorporated and how many people are in certain companies. You can also extract out subgraphs. So, in our original graph, we didn't have a relationship between that organization representing Netflix and the fact that it was in the US. We had to go through that other node to get there. So you can also say, construct me a graph where I want to know the org mapped into a particular country code where the other pattern matching. So that'll create that red line here, which didn't exist before, but you can construct that stuff out of a graph that doesn't exist, which might make sense for whatever queries you're working with. You can also do mutations, right? So if I wanted to, I could do an insert into a thing to add a new relationship onto an entity. Again, we don't need to get too hung up on all the syntax. But that's how we do RDF. Let's talk about property graph now. So in a property graph, it's a very different model. We have nodes or vertices, which are like the dots in your graph, and we have edges, which are the lines between the dots. And the dots and the edges, the nodes and the nodes and the edges both have types. So, for instance, Paul McCartney's type is he's an artist, and the United Kingdom's type is a place, an area, and the relationship is called from area. And nodes and edges can all have properties on them. So in this example, Paul McCartney has a gender and an age, and the United Kingdom has a type of country. And the relationship, the from area, has a metadata about it as well, right? So like Paul McCartney from the United Kingdom since 1942. And so you can work with property graph in a number of ways. Apache Tinkerpop is one of the most common, so that's what I'm going to talk about. So Tinkerpop and Gremlin concern themselves with both the structure of the data, how it's represented, and also how you query it, how you traverse the graph. So Tinkerpop is the open source graph computing framework, whereas Gremlin is the graph traversal language that you use to answer questions and mutate the graph. So Gremlin is an imperative language for traversing graphs. It's open source. A lot of different database engines support Gremlin querying of the data. And the way it works is it's composed of steps. So you're very literally saying, hey, database engine, here's kind of what I want to do. Start at this node, go over this relationship where maybe some value, find this other one. So you're explicitly saying, here's how I want you to travel across the graph to get me the data I care about. And you chain those steps together until you get your answer. And there's a number of different SDKs out there for working with Gremlin in different languages as well. So let's look at an example of this. So we'll look at use the MusicBrainz dataset, which describes information about songs and composers and places. So the graph might look like this, where we have artists. They're from different areas. Areas have labels are from areas. A work could be like a song or a poem or just things like that. A work has a composer, a lyricist, a writer. Artists can be members of bands with other artists. And so from this, maybe we want to say, show me the place where the writer of the song called I Miss You happens to live. So this is what that query looks like in Gremlin. So we start out with g.v. So g is like your graph traversal object. And so you say from this, .v means give me the nodes, give me the vertices. That's why it's called v. And then from that, I want to only give me the vertices that have a label of work, right? So that type of work. And then I furthermore want to look where the type happens to be, has a value of type called song. And then where the name is, I miss you, okay? So all of that is just going to zoom in and find this work. Has type song, has name, I miss you, is going to find a particular node in our graph that meets those characteristics. But next we're going to say in writer. What that means is where there was a relationship in to this node from somewhere else where that relationship type was called writer. So that all these graphs are directed, right? It goes from one node to another. So we're saying, give me an incoming relationship that's about a writer, okay? And then we'll say where it has the values of name. Oh, I've skipped a step, I'm sorry. Well, in writer, and then we say out from area. You can't, I didn't put that one on the bottom of the slide. So we'll say, find me the ones where the work is writer, okay, and then it's going to give me this particular one to give me the writer. It'll find the particular area that that writer is from, and then we can say, give me the name attribute on that area. And that's how I'll know where the composer of the song I Miss You happens to live. You can use a lot of different filterings. Gremlin is a really, really expressive language. There's a lot of different steps that you can do if you look at the documentation. But some of the basic ones are things like, I can say has or has not, which is like your where equals or where is not equal. We can look for specific types by saying if the graph or the node or the vertex or the edge has this particular label. We can deduplicate or we can limit our search results. We can also flip a coin. So that's a way of basically doing a randomized walk across your graph because you might not always want to go in exactly the same fashion depending on what you're querying. And you can use Boolean operations to combine things together. And you can do projections too, right? So the top one is just saying, if I know the particular ID of a vertex, of a node, I can say go to that node and then just give me its value map. That means give me all the values that node has. Or I can say, give me one property from that map instead of giving me all of them. Or I can say, find me all the artists, or all the nodes that have a label artist, where they have a name of the Beatles, follow the in relationship for members of band, and give me back their name and their gender so we can see George Harrison, John Lennon, Paul McCartney. I don't know why Ringo Starr isn't there. Don't worry, Ringo, I haven't forgotten about you. And tell me the names of the artists who used to work together in a band. So this is a really classic graph example, right? You might do something like that where you're doing self-joins as well. So find me the artists as A. So this is kind of putting a referential placeholder that we'll use later on in the query. So we say, find me the labels, find me the nodes with the label artist. I'll call them A. Find out what nodes were a member of that band. So go out from those nodes and then back in. So you're traversing that relationship out and in. We'll call those B. And then we'll give me A and B by name where the A does not equal B so that we don't see the link back to ourselves. So you can that's a really classical way that you would get kind of a collaborative network result out of a graph. You can do mutations too. I'm not going to walk you through all these. You'll have access to the slides later. But it's not just about querying. We can also insert updates. We can add edges between nodes that already exist, all those types of things. You can drop nodes and edges, everything you would expect. So the question is, which to use for your application? To use property graph or to use RDF? This is my helpful guide. You want to use property graph for Gremlin if attributes on relationships are valuable to you, because you can only do that in an easy way with property graph. You can do it sort of with RDF, but you have to jump through a bit more hoops in order to express metadata about relationships. So property graph is a more natural fit there. If you want different types of properties on the same node types, like a more flexible schema, property graph is for you. Or if you look at the RDF answers and none of those apply to you, you might default to property graph. So RDF, when do you use that? Definitely if you're building a knowledge graph, RDF is the natural framework and tooling to use for that. If you want to do inference on that knowledge graph to answer questions, again, RDF and Sparkle. Or if you're linking data together from the semantic web, like I talked about before. So great, you're excited, you're ready, you want to run a graph database. How are you going to do it? Well, there's a lot of graph database options out there. A number of them have some problems. I mean, nothing is perfect, right? But a lot of them out there have some issues. Some can be very difficult to scale. So they might work really well for just as you're getting started, small data set solutions. But when you put a lot of data in, you might start having trouble scaling them up. Or it could be difficult to set them up in a highly available fashion Or maybe it's not difficult or necessarily impossible to do that, but maybe you can't use the open source version of a particular tool for that. You need to use the enterprise edition now if you want high availability and uptime guarantees. That might be really expensive. Or you find a graph database you like, but there's limited support for these open standards I've talked about. Well, there's another option available to you. We have a product at AWS called Amazon Neptune. And this is a fully managed graph database that was purpose-built for this at AWS. So Neptune is open. We support both Apache Tinkerpop and W3C RDF graph models. So some database engines are going to make you pick one or the other. You can run either kind of workload on Neptune. It's really fast. So depending on the types of transactions you're doing with Neptune, if you're doing OLTP or more transactional workloads, where you're doing parameterized graph traversals, less than 3 hops with parameterized graph patterns, so more targeted queries. The target performance for Neptune is throughput up to 10,000 reads per server per second, with latency targets of less than 50 milliseconds. So it's pretty impressive targeting there. Of course, for OLAP or analytical type workloads and queries, things are going to take a little bit longer. These tend to be traversals of 3 or more hops on unbounded graph patterns with complex filters. Now, depending on your graph and your data set, these queries could take a while to run. But typically we see on the order of targeting anyway, support for hundreds of queries per second with latency targets that vary from hundreds of milliseconds up to minutes, depending on the nature of your query and your data set. I'll show you an example of one that's not a simple hello world query later on, and we can see it will take a few seconds, but it's operating on quite a big graph. Neptune, as I mentioned, is fully managed. I think this is really key. AWS, our goal is to handle all of the undifferentiated heavy lifting when it comes to building apps so that you can focus on what matters for your problem. Unless you are in the business of hosting graph databases, you should probably not be hosting your own graph database. Let another company like AWS handle that. We have a lot of operational experience in the industry. We know what we're doing. We know how to offer these things in a fully managed fashion, high availability, scalability, and security baked right in. So all those best practices you get just for using a fully managed service. Neptune supports 15 read replicas. I didn't mention that before, so you can achieve some pretty darn high query volumes through Neptune. And it supports encryption at rest and in transit as well, so you can keep your stuff secure. And it even does backups with point-in-time recovery. So everything you would come to expect from a fully managed service, you'll find it in Neptune. We have a number of customers using Amazon Neptune today. Siemens, they're using knowledge graphs for industrial designs, integrating with their support costs so they can figure out how to price support contracts better. AstraZeneca does drug discovery using Neptune and graph databases. I already talked about Thomson Reuters. Amazon Alexa uses Neptune, right? So you can ask Alexa for facts about the world, and those could be answered through a knowledge graph application. And so Neptune plays a role in that, empowering Alexa. I was recently in Sydney at an AWS Community Day, and I met with this company called Visalytics. They do knowledge graph work for customers in transportation, tourism, and economic development industries. They have a city builder solution that powers things like neighborhoods.NYC. This is really neat because I used to live in New York, and there's a service in New York where you can call a phone number and kind of complain about problems or things that need service. There's graffiti here, this fire hydrant is broken, anything like that. And neighborhoods.NYC provides a dashboard of insight on top of all of that data. And so that was really neat to later on in life meet a company that happened to be powering that style technology and happened to be using a graph for that as well. I was very excited about that. So it's demo time before we wrap up. Let me give you a demo. Here's what we're going to do. We're going to do product recommendations, but I wanted to get real. I didn't just want a little simple hello world. So I thought, okay, there is something called the Amazon Open Data Registry. This is a website that we have where we host large data sets with data about Amazon and about other public data sets that are out there. So I thought one of those data sets is Amazon reviews. So why don't I load some of that into Neptune and try and do that classic graph recommendation query with real data at Amazon scale. So here's what it looks like. The review data has basically just a bunch of rows. And those rows say this customer ID reviewed this product ID. The product ID had this name. They gave it this many stars. So from that kind of data, I extract out a graph that looks like this. We have customers, and they give reviews to products. You can get scoped review data set from this Amazon review data set. I play video games. I'm a nerd, so I thought I'm going to load the video games recommendations, review data set specifically. And just to give you an example, here's two people. We can't look at the whole network. It's too big. So particular example, and I added this to the network because I don't think my reviews and my friends' reviews are in there. But we can say, OK, Gabe gave Dota 2 5 stars and Daikatana 1 star. Cam gave Dota 2 5 stars and World of Warcraft 3 stars and Counter-Strike Go 5 stars and Daikatana 5 stars. So given this network, what we want to do is basically say, start with Gabe, find all the things that he gave 5 stars to. OK, that's just this. Find everybody else who gave 5 stars to this. OK, that's this guy. What else did he give 5 stars to that I haven't already reviewed? Oh, he gave 5 stars to that, but I already reviewed it, so no. He gave 3 stars to this, ignore. He gave 5 stars to this, so let's recommend that. And so I'll do 2 queries for you in a minute through Neptune. One that only queries this little isolated subgraph, just so I can test out the sanity of my query to make sure it works. And then we'll run that same query on one customer that has a lot of reviews, and we'll see a big graph traversal and a lot of recommendations come back in only a few seconds. All right, so let's go to the demo. Great, OK. So hopefully this is still active. Let's find out. I've got a Cloud9 ID here. This is our development environment that's in the cloud on AWS. What I like about it is I can do things like talk to my Neptune cluster is in a virtual private cloud, a VPC, that's not publicly accessible. So it's super secure that way, and I can only get at it from machines that sit inside that same VPC. And so this instance that this Cloud9 instance is running off of is inside that VPC. I'm also running Jupyter notebooks here. I like Python, and I think it's a good way to show code in demos. And so from that, I'm going to pop open my recommendation example. And we'll see if this works. So here, I'm just showing that I'm loading some dependencies to talk to Gremlin, or to use Gremlin from Python. Here, I'm going to connect to this Neptune cluster through a WebSocket interface and get that in a variable called G. Now, I'm going to declare some variables or some functions. And now we're going to find Gabe. And I'm going to ask for Gabe's recommendations. So I got back CSGO. So how did that work? Well, this is the query in Gremlin. So from a particular customer ID, find that node, call it target, then do a little side quest. Go from that user and go out, find all of that user's reviews that he did at all, and just call that products the target already reviewed. OK, that's the end of the side effect. So now we're still back at our original target node for Gabe. So now walk out and find all of his reviews with a rating of 5, and go into those vectors or those vertexes. Then follow the vectors or the vertices that reviewed those same products with a rating of 5 that were not already equal to target. And then from those people, find everything they rated a 5 where that doesn't include the things I already reviewed. Deduplicate any results because more than one person might have rated the same thing. So uniqueify my result set, give me back the product titles, and reify that as a list so that I can see the result in Python. So OK, what does this data set look like? Just the video game reviews. So there's 65,000 products in this graph. There are 1 million, just over 1 million customers in this graph. And there are 1.78 million reviews in this graph. So it's not hello world. It's not the biggest you could get. I mean, Neptune can handle a lot bigger than 1 million, but it's enough to show you something non-trivial. So I found a user that had done a lot of reviews because I figured that's going to be a combinatorially expensive query because we're going to have to go out to a number of products, find all the people who reviewed those, everything else those reviewed, and that's going to be a really large data set. So we're going to go out really big and then go back in. This will take a few seconds to run because this is more of an analytical style workload on a really big graph, but it only takes about, 5-7 seconds to return. And you can see we get back a lot of data here. So that's probably another indication that a lot of people are probably giving things 5 stars, so you're going to get back a lot of results here. But the point is, that worked. It was pretty fast on a pretty big data set, and this is the lowest powered Neptune instance we have. So it would be even faster if I used a more powerful box. So, graph database, all the things, right? Like, why not? Well, you shouldn't, right? Like, it should be a tool in your toolbox. But just because you can represent everything in a graph doesn't mean you should. Use graph databases when you want to find out how your entities are related to each other, or when you want to find relationship similarities between your entities, or if you want to discover centrality or influence scores between your entities, like the impact analysis example I told you about before. Probably not a good idea to use graph if you have things like, I want to search for all the entities with a specific attribute, right? In a graph database, it's going to have to traverse and look at all of the nodes for that. In a relational database, you've got indices that will work in a more efficient fashion for that. Or if you want to aggregate data from your entities, give me the average order amount for all my sales by month for 2018. That kind of query is not good for a graph, and it's great for our traditional RDBMSs. So use the right tool for the right job. OK, we're at the end. If you're excited by this and you want to learn more, I have a few references I want to point you to. You can learn more about Neptune here. So there's some Neptune samples on GitHub. We have a nice recommendation example on our own GitHub site. There's a great book called Practical Gremlin by Kelvin R. Lawrence. Funny thing about this, I was using this book to learn about Gremlin. And then like 2 weeks later, I was browsing our AWS org structure and looking at who's doing stuff with graph databases in AWS. And Kelvin Lawrence works at AWS. So it was a really nice confluence that, again, that I found an amazing resource that's for free online. And lo and behold, the guy who wrote it also works at AWS doing graph stuff. So it's a good resource, and it's by somebody who really knows what they're talking about. 2 talks, other conference talks that I liked, that I learned from, that I think are worth watching. One is called Graph Databases Will Change Your Freaking Life. It's fun, it's well presented. I give you more of an overview, like what I've done today, but from a different perspective. Another one is a practical guide to graph databases. Those are both worth the watch. Finally, the demo code for this talk I've already put up on GitHub. You can get it there. If we haven't scanned your badge, please make sure we do, not only so you can get $200 of AWS credits and all the slides, but also because we're going to ask you later what you thought of all of the sessions that you attended today and over the next 2 days as well. We care so much about that feedback. In our roadmap, over 90% of our product roadmaps on our services is derived directly from customer feedback. And similarly, in the presentations that we work on, we care a lot about what you thought about this and other presentations today. So please let us know what you thought. It's really valuable to help us continue to give you great content. Thank you for your attention. It's a real honor to get up here and share with you today. Have a great day, and I hope to see you around over the next 2 days here.